Welcome to our presentation. Today, I will share the latest progress in our research at ChromoLogic, funded by SBIR Phase 2 from ONR. Our project focuses on extending underwater working endurance by removing CO2 from diving systems using a membrane contactor-based CO2 absorbing module. First, let me introduce ChromoLogic. We are an innovation center dedicated to developing disruptive products and technologies. Our team comprises highly educated and excellent engineers and scientists working in multidisciplinary areas, including drug delivery, optical instruments, advanced sensors, green technologies, and more. You can see changes, progress, and creation almost every day here. Located in Monrovia, California, we have sufficient hardware resources to support our current work. Additionally, we maintain good relationships with nearby universities and research institutions, allowing us to share abundant human and instrumental resources for R&D. Having been established for over 15 years, ChromoLogic has developed an innovation model that generates $3 in non-SBIR revenue for every $1 in SBIR funding. We have spun off two companies based on our innovations. One of these spin-offs, Convisus, has achieved direct federal service sales to the U.S. Department of Homeland Security and provides supply chain services to the U.S. Defense Industrial Base. Additionally, one of our innovations has been successfully commercialized for ocular diagnostics with sales to Fortune 500 organizations. The Navy is seeking a next-generation underwater life support system. Before we delve into the specific requirements, let me provide some background on diving systems. As we know, the self-contained underwater breathing apparatus, known as scuba, is a diving mode that includes equipment with a gas supply and a CO2 scrubber, making it independent of surface support. Scuba systems with a closed-circuit rebreather, or CCR, do not release gas into the ambient water, making the diving approach silent and providing comparatively longer working endurance. Since no gas is released, the CO2 generated needs to be promptly removed by a scrubber to prevent excessive accumulation, which can cause hypercarbia. The current CO2 scrubbers use soda lime, with a maximum working endurance of about 4 hours. The main objective of this project is to extend the working endurance to 10 hours without increasing the scrubber's footprint or storing the captured CO2 within the rebreather. To design a system that meets the Navy's requirements, we translated these brief requirements into more specific parameters through literature and market studies. For example, the CO2 concentration should be maintained at less than 0.4%, based on the typical CO2 generation rate by a human body under moderate workload. The CO2 scrubbing rate should be more than 1.78 grams per minute. The newly designed scrubber should be comparable in size to typical soda lime-based CO2 scrubber canisters. Additionally, due to the unique underwater conditions, the entire scrubbing process should be passive, requiring no additional power or manual input. In this slide, I will provide a high-level overview of the solution proposed by ChromoLogic. The main technical challenge is that soda lime, packed in canisters as granules, has limited surface area. This limitation means their scrubbing efficacy cannot meet the safety requirements before being completely consumed, typically ensuring a working endurance of only 2 to 3 hours. It's important to clarify that during the working endurance, the scrubbing canister should maintain the CO2 concentration in the scrubbed air within a safe range. Some optimizations in the industry have been introduced by coating soda lime onto fabrics to increase the surface area. This approach allows more soda lime material to be used for CO2 absorption, extending the canister's working endurance to between 4 to 5 hours. A straightforward plan to address this issue would be to find a new solid absorbent that can capture the same amount of CO2 as soda lime, but with half or 1/3 the weight. However, no such materials currently exist that can be safely used underwater. Therefore, we propose a physical approach to scrub CO2 using seawater. As we know, compared to the CO2 generated by the diver, seawater can be regarded as infinite. Moreover, among the 3 main components of exhaled air, nitrogen, oxygen, and CO2, the solubility of CO2 in water is much higher than the other two components, making this approach highly selective. With the diver's movement, or ocean currents, the seawater around the diver can be continually refreshed, continuing the scrubbing process and extending the working endurance to at least 10 hours. Additionally, CO2 can dissolve into water and convert to carbonic acid. Although this process is comparatively slow, adding catalysts can accelerate it, enhancing the scrubbing process and enabling a more compact design. In addition to its application in CCR, this approach is also transferable to submarines, which require larger CO2 scrubbing capacities and longer working endurance. As a disruptive product, MCCAM has broad potential customers from various government agencies. As listed in this slide, they should all have an interest in underwater operations and waste gas treatments. Taking advantage of infinite seawater as an absorbent for CO2 scrubbing seems to be a good idea, but how can it be realized? Here, we will provide more technical details. As we know, to effectively dissolve gas into water, the size of the contacting surface area between water and gas is critical. In industrial applications, one typical approach to achieve a high contacting surface area is the membrane contactor. In this system, gas is split into ultra-small pieces as it flows through the porous membrane. Compared to flat sheet membranes, hollow fibers can provide much more surface area within a given package volume. Therefore, the MCCAM is mainly based on hollow fiber membranes, which constitute subsystem 1. As mentioned before, only part of the dissolved CO2 can be converted into carbonic acid, and this process is comparatively slow. To facilitate the reaction and increase water absorption capacity, a catalyst will be introduced into the hollow fiber membranes or HFMs as subsystem 2, particularly at the air-water interfaces. Unlike conventional soda-lime-based canisters, the use of seawater as a sufficient absorbent to extend working endurance can be regarded as the most innovative aspect of the MCCAM. The techniques to fabricate hollow fiber membranes and adjust their microstructures are well established in the industry, enabling us to tune and optimize their performance according to the application scenario and requirements. The catalyst to convert CO2 into carbonic acid is also a hot topic in academic research, which can facilitate the CO2 capture process. Based on newly reported synthetic catalysts, ChromoLogic has developed approaches to integrate these catalysts into the HFMs. In the table, the MCCAM is compared with current commercial products based on preliminary data collected from our Phase 1 experiments. With a comparable module size, the MCCAM has the advantage of being lighter due to its construction from porous hollow fibers without any preloaded absorbents. Its cost per dive is higher because of the complicated fabrication and integration process. However, this cost can be controlled as long as the module can be reused multiple times. Of course, the biggest advantage is its significantly extended working endurance. The main purpose of this project is to bring a disruptive product to the market. Here is our plan for commercialization. In the past few months, we have optimized the performance of hollow fiber membranes by adjusting their microstructures, such as pore size. Additionally, we have selected and evaluated catalysts and developed approaches to integrate them into the HFMs. Currently, we are planning to scale up the fabrication of hollow fibers to obtain sufficient quantities for the preparation of a full-size prototype. Therefore, the current technology readiness level of this project is between 3 and 4. Once the full-size prototype is obtained, both in-house and third-party evaluations will be conducted, which are scheduled for the next year. Here, we would like to share some recent progress and present our small-size prototype. A module containing 200 hollow fiber membranes was prepared, and its design schematic and photo image are shown here. Feed air flows into the inner side of the hollow fibers through a tube adapter, where CO2 is scrubbed. Afterward, the scrubbed air exits the prototype through another tube adapter and is delivered to a CO2 sensor. It's important to clarify that this small-size prototype is only designed for lab testing. The full-size prototype design will be completely different taking compatibility with CCR and the application scenario into account. The small prototype was tested with a setup that simulated ocean currents using gently flowing tap water. Feed air containing 4.5% CO2 was introduced at 10 milliliters per minute and 15 milliliters per minute into the fiber's inner side, and the scrubbed air was monitored by a sensor for its CO2 concentration. As shown in the figure, the CO2 concentration instantly decreased to 0.4% after passing through the scrubber prototype. When 5 liters of water were circulated in the system, the output CO2 concentration began to increase after about 30 minutes, indicating that the water started to become saturated with CO2, significantly affecting the scrubbing efficiency. Once we introduced fresh water continuously without circulation, the low output CO2 concentration could be maintained. However, when the feed air flow rate was increased to 20 milliliters per minute, the output CO2 concentration rose above 0.4%, which is no longer safe. The test results have verified the feasibility of underwater CO2 scrubbing using hollow fibers. They also enable us to estimate the required fiber bundle size to provide a sufficient CO2 scrubbing rate to match the metabolic rates of an active diver. When it comes to hollow fiber fabrication, ChromoLogic has established a benchtop fabrication process to support lab tests. However, to support the preparation of a full-size prototype, the current fabrication line needs to be scaled up by at least 100 times. This will involve a continuous fabrication design, as shown in the schematic. When the MC-CAM is commercialized, the key features, advantages, and benefits of this product are summarized in this table. The membrane contactor-based scrubber removes CO2 in the diving system primarily through a physical process, without any chemicals involved. The MC-CAM is safe for divers and reusable. The entire process is passive and can be completed via the diver's movement and ocean currents, requiring no additional power input or manual operation. Air breakthrough can occur when absorbent granules are improperly packed, allowing air bypass, or when the absorbents expire. However, with the pre-formed lumen channels in the HFM module and its long endurance, the MC-CAM has no air breakthrough problem. Catalyst-decorated HFMs exhibit significantly higher CO2 scrubbing efficiency compared to those without catalysts, further decreasing the scrubber's footprint. As mentioned before, the solubility of CO2 in seawater is much higher than that of other components. Therefore, the physical scrubbing process has high selectivity, and no loss of other gas components has been observed in our previous tests. With seawater as an infinite absorbent, the working endurance can be extended to over 10 hours. As mentioned before, the MC-CAM design can also be applied in submarines. Our plan is to complete in-house and third-party evaluations in the Phase 2 stage and identify customers who need long-endurance diving solutions. Additional funding or investment will be needed to assist in transferring the MC-CAM technology to submarines. In civilian market, MC-CAM can also find its niche markets, such as leisure diving, cleaning ship surfaces from fouling, constructing the underwater structures, rescue, education and training, underwater journalism and cinematography, and scientific research. Our industrial collaborator and potential customer is Inner Space Systems Corporation. ISC is a leading manufacturer and developer of highly innovative customized CCR systems with a proven track record of success. The company's CEO, Mr. Leon Scammahorn, is a distinguished 13-year veteran of the Special Forces with expertise in maritime operations and is the credited inventor of the Megalodon CCR. ISC will support us in identifying the required devices or alternatives for the tests, such as a sinusoidal mechanical breathing simulator and a hyperbaric chamber. Besides underwater CO2 scrubbing, the design and fabrication of membrane contactors developed in the MC-CAM project can also be transferred for CO2 capture in other applications. We are also seeking prime partners interested in this application. In closing, I would like to thank you for your time and attention. Please feel free to reach out using the contact information displayed on this slide. We look forward to collaborating with you.